Okay, today we're going to discuss about distributions because we would like to define an environment in which the delta Dirac function and its derivatives make sense. Okay, and so Dirac functions are generalized functions or distributions. So let's understand what does it mean. Okay, to understand, to define a distribution, we first need the concept of functional, of a functional t. And you know, for a electrical engineering student, this is easy to understand for you because it is basically a linear system. Indeed, we define a functional, a black box t, in which the input is a test function. I'm going to tell you it is now a test function, which belong to the space of test functions. And what are the properties of this test function? The test function, these are nice functions. What does it mean, nice function? They are, phi is defined on a compact support. It means that away from a given finite interval, the test function is 0. And then this function is nice. All its derivatives are continuous. So what does it mean? It simply means that this is a very nice function, and I can take any derivative and still get something, and still get nice functions. So with no discontinuities. And said that this is the input, then this operator acts on this function, on this test function phi, and it will return a number that we're going to call it t phi, or t within parentheses phi. Is the same notation. Okay, so this is a real number. So this is the function of t. It is a function of functions because the input is a function itself. It's a function. Okay, it's a test function, which belong to this very nice space of functions which are defined over a compact support, and they are nice. Okay, I can take any derivative and still get a continuous function. Okay, so nice, no discontinuity, everything is nice, and so this function, this operator, maps any function phi to a number. Okay. Said that, for example, if you to be a distribution is a functional which is linear and continuous. So now we need to understand what is the meaning of these two properties. Okay, and let me redefine. Let's rewrite here. So T is a distribution. T is a distribution if the functional t is linear. What does it mean, linear? If I take a linear combinations of test functions, when I apply the operator, I'm going to get the linear combination of the two operators applied to each test function. And this is pretty easy to understand. So linearity, that's what we want. That makes the life easier for an engineer. Then has to be continuous. So continuity now here is a little bit more delicate to define and also appreciate in meaning. But let's go slowly. So given a sequence of test functions phi sub n, which converges uniformly, that's the important things to understand. That is, limit as n tend to infinity of these test functions t converge to some function phi t, which in a uniformly, then limit as n tend to infinity of the operator t applied to each sequence, each function in the sequence, is also equal to t of phi. This is a strong statement, because what are we saying here? Now let's understand a little bit more what does it mean, this condition. This condition implies that, let me rewrite it in this way, that the limit as n tend to infinity of t applied to phi sub n is equal to t, open parenthesis, limit as n tend to infinity of phi sub n. That's what does it mean. It means that we can swap the operation of limit and the function and the operator t. They can be swapped, and I still get the same results. This is an important that's the key point in understanding the distributions, because this kind of swapping cannot be done every time in general. Okay, this is not a general property. Actually, it's going to be valid only if we have also uniformity in the convergence of this series. And that's only the key element to appreciate for understanding distributions. But now let me give you the meaning of convergence uniform convergence. What does it mean? The limit as n tend to infinity of phi n is equal to phi uniformly. It means that for each epsilon greater than 0 exists a delta which only depends upon the epsilon index, but it does not depend upon x, such that for any index n greater than delta epsilon, we have that in absolute value phi sub n of t minus phi of t is less than epsilon for any x. That is the important condition for uniformity. Indeed, to appreciate what this means, here I have the limiting function phi t, which is defined over some domain, can be finite or infinite. And then here we define the tube around the test function. So phi plus epsilon and phi minus epsilon. If the convergence is uniform, for any x, phi sub n is always within the tube. This is basically the tube of phi. Of course, no, for n greater than this index delta. And this is a strong, is a strong statement, because I can give you example of test functions of sequences which still converge but not uniformly, and the classical example is given by phi n of t is equal to Tn for t in 0, 1, and then 1 for t equal 1. Sorry, yeah, these functions here. They are well defined for any n in the interval 0, 1. And these are these functions. 0, 1. You can see that when n tends to infinity, the limiting function is 0 everywhere, except at 1 where it converges to 1. So the limiting function, it is equal to 0 for t 0 excluding 1, and then is equal to 1 for t equal 1. So phi is the limiting function is discontinuous. And that's one. And this series converges to something. You start with something that is continuous, and in the limit you will end up with something that is discontinuous, and the limiting function is discontinuous, and the convergence will not be uniform. In some sense, and that's it.